Amy, and Minkai. Today we'll present our project on latent denoising diffusion probabilistic models. Diffusion models are powerful for image generation but face three main challenges. First, the inference process is extremely long, often requiring thousands of steps. Second, operating in the pixel space makes computation expensive. Third, it's difficult to guide the generation towards specific outputs without an external control. These challenges limit its real-world applications. Our goals are threefold. First, we want to improve the efficiency by optimizing for faster and scalable generation. Second, enabling better control over the outputs through conditional generation will be good. Third, we want to enhance the image quality and diversity while reducing the computational cost. Addressing these challenges could have broad practical impacts, such as enabling low latency content generation for some live applications, applying conditional generation to specialized fields like cartoon generation, and also making the deployment on resource-limited device feasible. In our project, we re-implemented 4 key components from the foundation papers on diffusion models. First, we implemented DDPM, which uses a fixed forward noise schedule and a learned denoising model. Second, we implemented DDIM, which accelerates inference by making the denoising process non-Markov-Avoidant. Third, we moved the denoising process into LDM, which operates in a compressed latent space rather than pixel space, greatly reducing the computational cost. Finally, we integrated conditional image generation with CFG, enabling the model to generate images aligned with specific class labels without needing an external classifier. We used 2 datasets, Cypher10, a small dataset with 10 classes, for testing, and ImageNet 128 with 100 classes to generate more complex and diverse images. To stabilize training, all the pixel values are normalized. The latent space is also scaled to maintain unique standard deviation. This helped the model converge faster and generate higher quality outputs.
Now let's walk through our training pipeline in detail. We start with the dataset. Each image first goes through pre-processing. Then, at each iteration, the data loader randomly samples a timestamp t for each image. This timestamp represents how much noise will be added. Based on the sample t, we add noise to the latent representations. The resulting noisy latents, together with the timestamp t and possibly a conditioning vector c if CFG is enabled, are fed into the UNet model. The UNet is trained to predict the added noise. We then calculate loss, and the loss is used to update the model weights inside the training loop through backpropagation. Now, let's look at our inference pipeline. First, we run a conditional image generation pipeline. We start from pure noise in the latent space and progressively denoise it over multiple steps. If conditional generation is enabled, like in CFG, the model is guided towards specific class labels during the denoising process. After the denoising process finishes, we obtain a latent representation of the final image. Since we scale the latents during training, we need to rescale the generated outputs back to their original distribution. Finally, we decode the rescaled latent outputs using a pre-trained VAE decoder. Here, we show outputs from DDPM without CFG on ImageNet 128. The images are diverse, but sometimes lack clear structure or alignment with specific classes. DDIM greatly accelerates inference by skipping intermediate noise steps. You can see that DDIM outputs maintain comparable image quality to DDPM, but with many fewer steps. After enabling CFG, the generated images are much more faithful to the target class labels. CFG improves both controllability and visual clarity. In conclusion, DDIM offers faster inference while maintaining quality. Enabling CFG enhances control and fidelity of generated images. In our final report, we plan to explore more advanced training methods like improved noise schedules to push generation efficiency and quality.